Hello Year 10s. We're starting a new topic today, which is electric circuits. And this is going to be building on the work that you did back in Year 9. So hopefully you haven't got rid of your Year 9 exercise books, because this basically continues onwards from Year 9. Now, back in Year 9, you looked at basic electric circuits, you looked at series circuits. So we are going to start off this lesson with a reminder of series circuits. In Year 9 you also looked at the definition of terms like potential difference, current and resistance. So we'll have a bit of a reminder of that in this lesson as well. Beyond that, we need to extend to circuits that are a little bit more complicated than series circuits. So we'll then look at parallel circuits, which is additional work that you didn't do in Year 9. But just as a very quick reminder of the Year 9 work, we're just going to have a look first of all at a series circuit and what a series circuit is and what the measurements are that we can take from a series circuit. So I've got one set up here. I've connected it to a DC power supply. Now, in the textbook, you'll usually see a battery being used as the power supply for a DC circuit. That's absolutely fine, but we don't have that many batteries available in the department, so we use power supplies usually instead. So we've got a DC power supply representing the battery. We've got two light bulbs and we've also got a switch. So if I go over here, I can switch the switch on and off. And that is a series circuit. It's pretty straightforward. It's just a loop with all the components connected in a line. So the two light bulbs are connected as part of the main loop of the circuit. So all the current goes through both light bulbs. Now let's just remind you of a few things that you can measure from a series circuit. So the first thing I'm going to talk about is potential difference, which is sometimes referred to as voltage. So you would measure potential difference with one of these. Okay, so you would measure it with a voltmeter. And the potential difference from one side of a component to the other side of the component is how much energy is transferred by each coulomb of charge that passes through. So if 1 coulomb of charge passes through this light bulb and it transfers 5 joules of energy, obviously into light and heat, then we'd say there was 5 volts of potential difference across the light bulb. Okay, so when you measure potential difference, you don't put the voltmeter in the circuit, you put it across the component that you're looking at and measure the potential difference across it. So that's what I'm going to do with this voltmeter here. So I'm going to connect it across here. And we've got a reading of 6.94 volts. I'm then going to connect the voltmeter across the other light bulb. And we've got it's flickering a little bit, 6.4 volts across the other. So 6.9 volts, 6.4 volts, they're very similar. If they were absolutely identical light bulbs, we'd have the same voltage across each one or the same potential difference across each one. But if you add up 6.9 and 6.4, you would get 13.3. And that's interesting because if I measure the potential difference across both of these light bulbs together, I should get about 13.3. Now that is assuming that there's no resistance in the wires that are connecting them. So it might be slightly higher than 13.3. But there we go. It is a little bit higher than 13.3. It's 13.8. But you can see that the voltage adds up, or the potential difference adds up. So if I take the potential difference across that and add the potential difference across that, you'll get the potential difference across both light bulbs. So in a series circuit, the voltage gets split up. You can also see the reading on here. That's the potential difference being given out by the power pack. Now it does say 15 volts, but again, we do assume that the wires in a perfect circuit have no resistance. These wires will have some resistance, and these connections will have some resistance, which means that that's a little bit higher than the 13.3 we were expecting across here. So the voltage supplied by the power supply, or the potential difference supplied by the power supply, will get split up by the two components, which are transferring energy out of the current. So that's measuring the voltage in a series circuit. So the voltage gets divided or split by the components. The other thing to measure is current. Students tend to understand what current is a little bit easier than potential difference. So to measure current, you need an ammeter. So that's an ammeter. And if I put an ammeter in the circuit, I measure the current. Now, current is how much charge passes a point in a second. Charge is measured in coulombs, so 1 amp means 1 coulomb per second of charge passes through the ammeter and at that point in the circuit. So that's what we mean by current. So if I place the ammeter at a strategic location within this circuit, so I'm just going to put it here. I read 1.2, I don't know if the camera can see that, 1.27 amps of current at that point here. Now, interestingly, in a series circuit, it doesn't matter where you put the ammeter, it will always read the same current. So if instead of putting the ammeter here, I put it here, or if I put the ammeter over here, let me try that, it should read about 1.27 amps. Current is not used up by components, it just travels around the circuit in a series circuit. There we go, it's very close, 1.29 amps. So, current stays the same all the way around a series circuit, but the voltage gets split up. So if we had 12 volts coming out of the power supply, if these are identical, you'd have 6 volts across that, 6 volts across that. If they weren't identical, you could have 9 volts across that, 3 volts across that component. So that's the basic rule in a series circuit for potential difference and current. What you've also got to remember in a series circuit is that the resistance of the components adds up. So resistance is calculated by doing the potential difference divided by the current, and it's measured in ohms. So if this bulb was 2 ohms, that bulb was 2 ohms, they would add together and produce a resistance of 4 ohms. Now you will get some notes on this, so don't worry too much if you haven't quite taken all this in. It is a year since you did it last, so it's a bit of a reminder. But that's measuring potential difference and current in a series circuit. Remember that the ammeter always goes in series, so it goes in the main loop of the circuit, whereas the voltmeter, if you're using a voltmeter, will go across the light bulb. So that's basically a series circuit. The other thing to talk about before we go on to parallel circuits is, well, what are the advantages and disadvantages of a series circuit? Well, the advantage of a series circuit is that they're quite simple. Okay, you just have one wire that goes all the way around, or it's one loop. So simplicity, less wiring. However, there are disadvantages in series circuits as well. With a series circuit, you can't turn each component on and off independently. Now I've got a switch here, and you can see it just turns both components either on or off. So you can't independently switch the components on and off. It's either all of them or none of them. Similarly, if one of these bulbs was to fail, so if that bulb blew, no current would go through it, it would be a break in the circuit, that bulb would go off as well. So that's a disadvantage really of a series circuit. You can't independently control the light bulbs. I'll show you another disadvantage of a series circuit as well. Supposing I wanted more than 2 light bulbs, supposing I wanted 3 light bulbs. So I'm just going to move that light bulb here. I'm going to bring in a 3rd light bulb. If I connect this 3rd light bulb in, you'll see immediately what's happened. Now the 3 light bulbs have come back on again, but I think you'll notice that they're all dimmer than the 2 light bulbs previously. So every time you add a component, the total resistance of the circuit goes up, which means that the current going through the circuit, remember the current would be voltage divided by resistance. If the resistance has gone up, the current going through the circuit drops. And 4 bulbs, 5 bulbs, 6 bulbs, however many bulbs you add, the current would keep on dropping. It's actually, you can see how it's dropped there, it's dropped to 1.03 amps. It was nearly 1.3 amps before. So that's another disadvantage of a series circuit. As you add more components to the circuit, the current going through drops as the resistance goes up. Okay, so that's series circuits. Now obviously we're going to be doing a comparison between series circuits and parallel circuits. Now you haven't met parallel circuits before, unless you did a bit in Key Stage 3. So what do we mean by a parallel circuit? Well, I'm going to take the ammeter away, just as a demonstration first of all, and then I'll set up 2 of these light bulbs in a parallel circuit. I'll also take the switch away. Okay, so first of all I'm just going to connect one of the light bulbs straight to the power pack. And you can see that light bulb has come on extremely brightly, in fact so brightly I'm worried it might blow, so I'm just going to turn down the voltage a little bit. Okay, so that light bulb has come on very brightly. Now that one light bulb is connected in series, if you like, to the power pack. Now I'm going to put another light bulb in. Now remember before, when I put another light bulb in, I put it in series, the light bulb got dimmer. Well, what about instead of putting it in series, if I put it in parallel, which means that I connect it across the first light bulb. So rather than connecting it in a loop, so rather than putting a light bulb here, I'm going to connect it around the first light bulb, so more in a sort of ladder arrangement. So there we go. So I've put a second light bulb in parallel with the first light bulb. Now what you would have noticed is that actually they're both pretty bright still. They haven't actually dimmed. So the current going through each light bulb stays the same. And I can extend that again. Now that light bulb's gone off, probably because I've got a bad connection here. Okay, yep, almost certainly. Always check your wires to see if you've got a bad wire. Now I've probably got a bad wire there. It's not a bad bulb because we know the bulb's working. Oh, there we go, that's come on. I'm going to try it with a third light bulb as well. So let's try it with a third light bulb. Okay, and the third light bulb should come on. There we go, bad connection, but the third light bulb has come on. And you can see that all 3 of them are bright. If I turn this up, you can see they'll all get extremely bright. So that's a parallel circuit where you put each component on a loop around the other component rather than in the main loop of the circuit. So these components are arranged sort of ladder fashion. What are the advantages of parallel circuits? Well, for one thing, you can switch each component on and off separately. So if I put a switch in here, for example, now this switch is just connected to this light bulb here. Oops. I've just got some bad connections there, it's nothing to do with the circuit. There we go. You can see that I can switch this light bulb on and off independently. And when I switch this off, it has no effect on that bulb and that bulb. Okay, Each light bulb can be controlled completely independently. Each light bulb stays the same brightness when you add more light bulbs in as well. Now there is a disadvantage of that because you're drawing more current out of the power supply. So parallel circuits do have a bit of a disadvantage as well. If I was to put 20 light bulbs in parallel, I would probably flip the trip switch, the circuit breaker in this power pack. Got some dodgy wires there. Okay, so that's a parallel circuit. Now the other thing you have to learn about is how to measure current and potential difference in a parallel circuit. So I'm just going to do that now. I'm going to take one of these bulbs out just because having 3 bulbs in is a bit confusing. So we'll just make a parallel circuit just with 2 light bulbs. Make sure we get the second light bulb working again. Okay, so here's a parallel circuit just with 2 light bulbs. Let's switch it on. There we go. So that is working absolutely fine. Measuring the current and the potential difference in a parallel circuit. Well, first of all, the current, we need a voltmeter again. If I measure the potential difference, I need a voltmeter. If I measure the potential difference across here and the potential difference across here, it will be the same in theory as the potential difference across the power supply or across the battery if you were using a battery. Now I'll just prove this. Now hopefully the bulb will stay on and not go off. So here we've got 11.5 volts. And if I put it across this one here, we've got 11.7 volts. It's slightly higher because again we're assuming that the wires have no resistance, where in fact the wires do have a bit of resistance. But it's pretty much the same voltage across this light bulb as this, about 11.5 volts. Now if they'd been in series, they would have split that voltage. That's the voltage from the power supply. Each bulb is getting the same voltage that the power supply produces. If you put these 2 bulbs in series, one's going again. There we go. If you put these 2 bulbs in series, then they would have split that 11.5 volts, and so you would have got less than 6 volts across each one. So that's the first rule about parallel circuits, is that the voltage across each component is the same as the voltage across, well, the same as each other and the same as the voltage across the power supply, the potential difference across the power supply. So that's voltage. What about current? Okay, so I'm going to take my voltmeter away and I'm going to bring my ammeter back. So here's my ammeter, and what I'm going to do is I'm going to measure the current at different points in the circuit, and what you'll hopefully see is this. You'll get a large current coming out of the power supply, and then at the joins it will split, and if these bulbs were identical, half the current would go through that bulb and half the current would go through that bulb. So it's almost the opposite rules from a series circuit. Remember, in a series circuit the potential difference got split but the current stayed the same. In a parallel circuit the potential difference stays the same but the current splits. So let me try and show you that. So I'm going to measure the current just going through that one light bulb there. So to do that I'll have to take this connection out. I'll stick that in the ammeter there. I'll stick that here. And what have we got? 1.69 amps. So 1.69 amps through that light bulb there. So I'm going to take the ammeter back out again and put the ammeter somewhere else. So 1.69 amps through here. So how much current have I got going through the other bulb? Well, if they're identical, I would have about the same current. Now, they won't be exactly identical, but let's check. So and what I'm going to have to do is going to have to take all of this join out here. I'm going to have to stick that in there. I'm going to have to take this wire. Then I think I'll put it there and then hope everything comes back on again. Okay. So it's actually 1.6. I don't know if you can read that. Probably can't read it, but it is 1.69 amps. So you had 1.69 amps through there, 1.69 amps through here. Now that's close enough, 1.7, 1.7. If you add 1.7 and 1.7 up together, that gives you 3.4 amps. Now I reckon that to feed these two light bulbs with 1.7 amps, you had to have 3.4 amps coming out of the power supply. So let's check that again. So remember, 1.7 amps, 1.7 amps. If I check what's coming out of the power supply, and 3.38 amps, which is exactly the current going through that plus the current going through that. Of course, these two didn't have to be the same. You could have had 2 amps going through that and 1 amp going through that, and then that would have added up to 3 amps. But these two bulbs are very similar. Okay, so that's the rules really for parallel circuits that you have to remember. The voltage is the same across each one, but the current splits up at the join. It's something that's a bit easier to explain with a circuit diagram because it's a bit neater than having all these wires sort of flapping all over the place. However, it's also good to see it actually set up, given that you guys are at home and that you can't actually do this in the lab for real. If we'd been in the lab, we would have obviously had you building these circuits and taking measurements yourself and finding this out yourself. We obviously can't do that, but that was a demonstration of potential difference and current in series and parallel circuits. Series you did last year, so it was a bit of a reminder. Parallel is something new. So often they'll ask you, why is a parallel circuit better than a series circuit? Well, all you've got to say is, one thing you've got to say is that you can switch each component on and off independently. Another thing that you can say is that you get the same voltage across each one as the potential difference across the power supply, and that doesn't change when you add more components in. So in the case of these light bulbs, they'll stay the same brightness. Okay, that's it. I'm going to give you some notes, and I'm also going to give you some homework, and this is going to be homework for this week, so I would like it in, I think, by Thursday. So Thursday evening, if that homework could be sent back. Okay, that's it. Thank you very much for listening.